Great. Good morning, everybody, and thanks a lot to the organizers for this wonderful opportunity to present my research. I'm now starting a group at the University of Regensburg, but the work I'm going to present to you today was done at the Columbia University. So if we think about matter, one of the fundamental interactions between the particle and matter is Coulomb interaction, so basically repulsion and attraction of charges. And the consequence of it is that the fundamental excitation in matter in many cases are not single particles, but rather some sort of a many-body states. And obviously, in many occasions, these states behave quite differently than single electrons and can exhibit a variety of collective phenomena. As I will show you later, they can couple strongly to light and can change the properties of material quite a lot. In addition to the interaction, the matter itself can be nanostructured in a variety of ways, and most of us are familiar with a lot with a large range of such systems, ranging for, let's say, zero-dimensional quantum dot systems where the movement of carriers is restricted in all three dimensions. They are one-dimensional systems. Most prominent, arguably, are the carbon nanotubes, where the carriers basically move along one line. And finally, there are two-dimensional systems, where the carriers are basically free to move along two dimensions, but the movement is strongly restricted along the third one. And in this talk here, I would like to present you some of the properties of states arising from the Coulomb interaction in this class of materials. And specifically, I would focus a lot on the optics, on the interactions of the states with light. So what I'm going to do is to show you first and present you the systems we're working on, discuss their properties, and show specifically the excitonic particles. So, and in the second part, last part, I will show you how we can tune these many-body states using different approaches. So the class of 2D materials stems from basically a large variety of bulk van der Waals crystals. And these crystals are such that the atoms are arranged in planes with a very strong bonding inside the plane and a very weak van der Waals interaction between the planes. Which means that by a variety of means we can isolate even single layers of such material, which would basically be an atomically thin quasi two-dimensional layer with a thickness on the order of a single unit cell of the host material, usually below 1 nanometer. And I guess the most prominent example of this material is actually graphite, where this weak van der Waals forces allowed us to use it as a writing tool. And as we know, the single layer of it is called graphene, and it received quite some attention over the last years because of its quite extraordinary properties. However, nowadays, if we look at the, let's say, periodic table, there are many more materials, many more van der Waals materials which can be produced as single stable monolayers. So graphene, which is a semi-metal we find over there, there's boron nitride, which is an insulator, a class of 3,4 chalcogenides and 2,4 halides, which are semiconductors, a family of transition metal chalcogenides, which can be metals, semi-metals, and semiconductors as well as more exotic systems as, let's say, bismuth selenide, a topological insulator, there are superconductors, magnetic materials, and many, many more which can find a place in the slide. So a large variety of systems. Today, I will talk about the semiconducting family in these materials, the so-called transition metal dichalcogenides. If we look at these layers from the side, there are the metal atoms in the middle, which are usually molybdenum and tungsten, surrounded by two chalcogens atoms, sulfur, selenium, or telluride. So the thickness of this layer is nominally on the order of 0.6 nanometers, and they can be produced in a variety of ways. So one is sort of the classic mechanical exfoliation, so basically just taking a tape and sort of peeling off a single flake, which usually is sort of with the size of the crystal relatively small, in the order of like tens of micrometers, but there can also be chemically grown as large single crystals. And if we think about the electronic band structure of these materials, and we look at the real space from the top, we find the basically hexagonal honeycomb lattice similar to graphene, which means the Brillouin zone is also hexagonal, and the important points will be the center of it, the gamma point, and the edges, which is key. So these materials were studied quite extensively in the 60s and the early 70s of the previous century. And if we look at the band structure, we see it's a semiconductor, so there is obviously a gap between the valence and conduction band, but it's also an indirect one, which means that the maximum of the valence band and the minimum of the conduction band are displaced in momentum space. And for the optics, it means this transition basically cannot be accessed with one photon because of the lack of the momentum. Now, if we decrease the thickness of these layers, we can think about it in terms of quantum confinement effect. So basically, the electronic levels will move depending on their mass in the z direction. And since the mass is not constant and is different for different values, different position in the Brion zone, the bands will move differently. And what happens is the following. We go from bulk to full layer to bilayer. These levels start to shift apart, and we arrive at the monolayer with the direct transition, lowest transition at the K points of the Brion zone. And that had quite a few implications. First of all, now our lowest transition can be optically accessed. It couples strongly to light. It can absorb individual photons. And the other consequence was that because of the breaking of the symmetry in such a case, people calculated and experimentally verified a very strong coupling between the spins at K and let's say minus K points. And with a lot of interest generated by this property that the spin and value are coupled. However, today in this talk I would like to focus on the light absorption and the particles it originates from. So what you see here is an absorbance spectrum of such a layer at room temperature. So basically the amount of light absorbed as function of the photon energy here somewhere between sort of the red and the blue spectrum of visible light. And you see two things from the spectrum. First of all, the absorbance is very, very high. So we get 10 to 20% absorption in a material which is basically as thin as 0.6 nanometers. So it's quite a lot. And the second thing, you see that, sure, we have an optical gap over here, so basically zero absorption there, but there is a lot of structure in the spectrum, right? It's not just sort of a single smooth onset of absorption, but a lot of very pronounced peaks. And these peaks, as I will show you, stem from the particles called excitons, Coulomb-bound electrons and holes. And if we extract the strength of the absorption for such a peak and compare it with more conventional materials, such as gallium arsenide, for example, or 2,5 to 6 materials, we see the coupling to light is 10 to 100 times stronger. So with quite some consequences. So the question is why it is the case, and of course, what can we learn about these particles? And to do so, let me first introduce it a bit, and using a very sort of simplified picture, what an exciton is about. So if we look at the crystal structure, we zoom in, we sort of have our atoms sitting at the lattice sides, and again, in a very basic picture, we can imagine the valence electrons are sort of sitting there and holding the crystal together. Now, as a semiconductor, if a photon with a proper energy arrives, so the energy is high enough to excite such an electron into conduction band, it basically then can freely move through the crystal. The rest of the electrons, and of course the positive ions, behave in a way, as we know that these missing electrons can be seen as a positive charge, a hole, which can propagate through the crystal in a similar way as the electron does. Now, since these particles are charged, due to the Coulomb interaction, they are attracted to each other, and if the conditions are right, they will form a bound state called an exciton. So now basically, these two particles will propagate through the crystal together as sort of a single entity. In the momentum space, the wave function of the exciton will look something like that. So it will be a superposition of a variety of electron and hole state close to the respective band extrema, and here basically the size of the circle roughly indicates the amount of the contribution. In terms of, let's say, atomic physics, we can imagine exciton to be akin to an atom, basically a hydrogen atom, very similar to the donor states from the previous talk. However, there are also trines where an exciton can bind additional charge, which is something like an ion, and it also can bind, so basically two excitons combine together to form a molecule, a biexciton. And as you saw already, excitons are quite important for optics. They usually define the optical band gap and have this peak-like feature added, different from the quasi-particle bandgap. Yeah? So different from the sort of spectral position and energy of freely moving particles. In transport, if we think about some sort of a photovoltaic application where photons come in and create excitons, now these are neutral particles. We cannot use electric fields to steer them, so basically we need to propagate to some interface and dissociate. So when people design solar cells in the materials with basically which are strongly excitonic, a lot of organics, there is a lot of considerations about this process. In addition, there are things like multi-exciton generation, larger excitonic complexes, or potentially even Bose-Einstein condensation of these particles. Now, to learn about the properties and the structure of the excitons, there is a variety of ways, and one of the traditional one is to look basically at the structure of internal excitonic states. And for that, basically, I would like to use sort of a Bohr-type picture. So we have a hole and an electron more or less revolving around it in its ground state, which, as I have shown you, can be accessed with a photon and gives us this very strong optical absorption in a single. However, similar to a hydrogen, there is not only a ground state, but a series of excited states, so basically sort of next orbits, here denoted by the main quantum number, which also provide an optical response at higher energy, because these states are basically lower binding and slightly quite reduced oscillator strength. So basically they couple to light, but much weaker than the ground state. And there is a whole series of the states, which one can call Rydberg series, up to the ionization continuum, where the electron and hole are not bound anymore. That will be the quasi-particle transport bandgap. And again, the latter of the states will closely resemble an atomic scenario. Now, if we would measure, for example, the position of the states, we could extrapolate to the position of the bandgap and determine, for example, the binding energy. So one of the most fundamental properties of these particles, basically how strong electrons and holes are bound together. And we did this from one such thin flakes of these 2D semiconductors. And what you see here is a derivative of a reflectance signal. So basically every peak has this derivative-like shape with a very strong response from a ground state exciton. At higher energy, we observe the whole series of states up to n = 5. And that allows us to extract the position of the bandgap, which will be roughly over there, and the binding energy of over 300 milli. So usually in solid-state systems, or more in particular in inorganic semiconductors, the binding energy of these particles is relatively small. So in gallium arsenide, it's on the order of 10 MeV. So this number is 30 times more than what we will have, let's say, in gallium arsenide, but also more than 10 times the fluctuations in room temperature, which makes these complexes extremely stable to a variety of conditions. And of course, we were not the only groups looking at this, and there are a few of our colleagues with very similar results. So now the question is, as this binding energy is so large, and as I mentioned before, the coupling to light is very strong. What is the reason? So basically, why is the coupling so strong? If we consider an electron and hole confined in this layer, the first reason is, of course, quantum confinement. So if we solve a hydrogen problem in 2 dimensions instead of 3, we get the factor of 4 enhancement in the binding energy from the dimensionality straight at, from the dimensionality. The second reason is the very weak dielectric screening, because of course the charges and the electrons and the hole are confined in the layer, but the electric field is not. So basically, in a very simple sort of classical picture, you would imagine the field lines penetrating both the material, but they also permeate the surroundings. And now the surroundings is either a weakly screened substrate, vacuum, or air. So the screening of the electric field is very, very weak. It means the coupling between the charges is very strong. In addition, as it was worked out by Leonid Keldysh in the 70s, the Coulomb interaction in such a system will deviate from the form we would usually know, the 1/r dependence. And the reason is that, again, in the same picture, imagine you pull these charges apart now. And when you do so, larger and larger portion of the electric field will permeate the surroundings and less the material itself. Which means that the screening of the electric field will be distance dependent. And if it's distance dependent, if it's not a constant, the law will not be 1/r. And all of that can be worked out theoretically and basically matches to what we measure in the experiment quite well. So So here you see the energy of the excitonic state as function of the quantum. Now, this theoretical approach reproduces, as you can see here, the energies, but also the oscillator strengths, which means we can put some trust into the wave functions. And this looks the following way. So here you see a radial probability of finding an electron when the hole is fixed at 0. So here we learn two things about it. First of all, this is a proper so-called Wannier mode exciton. Basically, it means that the wave function of this state averages over many, many lattice constants. In comparison to so-called tranquil exciton, where basically they sit on one unit cell, quite often in organic materials. But secondly, the Bohr radius is still very small. So it's still on the order of, if we extract this value, let's say here from this maximum, it's on the order of 1 nanometer. If that would be gallium arsenide, this peak will be roughly over here, around 10 to 16 nanometers. It means that they're very close together, and that naturally explains the very strong light-matter interaction, because the overlap of the electron and hole wave function is very large. All right, so what I have shown you now is that the optical properties of this materials and the very strong absorption, the 10–15%, mainly originates from this excitonic complexes. And one of the questions could be, how can we tune it? Yeah? And of course, again, there is a variety of ways to do so using all sorts of external fields. And I will present you two ways to do so. And the first one is electrical injection. So basically, what we want to do, we want to study what happens with the material if we just insert one type of carriers either in the conduction or in the valence band. And to do that, we use sort of a capacitor type structure. So we have our monolayer over here, and there is a thermal oxide and the silicon with the two contacts. And we can do optics. So we look here at the reflection and look at this excitonic feature. Now this is a bit looks a bit strange. It's not a symmetric peak, but the reason here is just because of the optical interference of this 300 nanometer silicon dioxide layer. Yeah. But that's basically in the dielectric function. That would be a single Lorentzian type feature. Now, as we increase the voltage, we will start to sort of flood our materials with electrons, and the following happens. There is a second peak arising at the lower energy side. And this peak is identified as the trion, as a charge state of the exciton. And such a particle, of course, was studied quite a lot in astronomy, so the charge ion of hydrogen, and was also predicted by Lambert in 1959 to occur in semiconducting system. However, as you can see here, it took almost more than 30 years to actually find it, and these are basically the reports from this material system. And the reason was that usually these particles have very, very small binding energy, so you need to have excellent material quality and very low temperatures. However, in this case, as we can extract it from the distance between the two peaks, the binding energy, again, is very high. It's on the order of 30 millielectron volts, which means now we can access regimes with this charged excitonic states previously were very hard to obtain. So basically, at elevated temperatures, at temperatures where disorder potentials play a lesser role, and we can think about excitonic currents in certain phenomena. Yeah. But if we look at the optics in this range, what we see first is the more electrons we get, the more trions we can excite, then we can basically, the transition, the oscillator strength is tuned from the neutral to a charge exciton.
What's the spin of the trion?
I don't know. But I'm sorry, let me just, let's postpone this question. So there are, let me say, maybe rephrase my answer a bit. There are a few trion configurations in the systems. Okay, so therefore, it's basically depends on the alignment of the bands, it depends which configurations are there. So usually what you get, let's say, a whole, and so you get all sorts of singlet and triplet state for the neutral exciton alone, and then you can have an additional spin of the trion, but you basically get all configurations stable. Yeah. So therefore, of course, in the given experiment, we see just two peaks, right? So we can't tell, but using magnetic fields and such ways, one can determine that. In this particular case, the configuration would be the valence, so the hole is like this, the electron is like that in the neutral exciton, and then the other electron has spin down. Alright, but let me move on. So in addition to the trions, we can also look at what happens with the excitonic particles themselves. And to do so, again, we can look at the excited states as function of this gate voltage. And what we observe, as the gate voltage is increased, these energies shift in the following way. Yeah? So what we see is basically that the states of the exciton and the band gap shift like this, the more doping we have. So we see a decrease of the binding energy, and the states shifting together, and a stronger normalization of the band gap. And in this particular scenario, which is related to the band structure of this material and the way we dope it, the main reason for this effect is screening. And screening in the classical way we can imagine like this. Let's say we have a charge, an electric field, we add electrons, the electrons will arrange themselves around this charge, and from a certain distance on, the so-called characteristic screening lengths, they will screen the electric field, so the charge will appear neutral. And of course, all phenomena associated with Coulomb interaction will be weaker, such as the binding energy. Yeah. So as you can see here, the binding energy from the ground state and excited states as function of the electron density. And at some point, of course, the screening will be so strong, and it's sort of, and one way to imagine it, basically the screening length decreases below the exciton radius. So the electron and hole basically don't see each other anymore as charged states, and that will be the called mode transition, a term which is borrowed from the transition from insulator to metal, which means we're not in the excitonic regime anymore, we are in the regime of plasma. One thing to point out here, this happens at very high exciton densities, right? This happens between 10 to the 13 and 10 to the 14 square centimeter, which means and for gallium arsenide, again, this point will be somewhere down there. Yeah? So, and here again, we need this very high density because the radius of the exciton is very small. Yeah? So basically, and so this sort of ties in with what I want to show you in this last topic, which is how to change the optical properties and how to change the states when using intense optical excitation. So what we want to do here is we use a short, very intense laser pulse to inject a lot of electrons and holes into the material. In this particular case, we start with undoped, basically more or less system, 70K. So we have again an absorption, this very strong excitonic peak. And now we will inject an electron hole density as high as roughly 1 electron hole per square nanometer. So very, very high density regime. And what will happen is the following. So I will show here the spectra after the excitation. As the excitation pulse arrives, the exciton transition is more or less flat. It disappears. And then only on the order of a few picoseconds and start to recover, and then after hundreds of picoseconds, we get the properties of our initial material back. And we can do that not only at low temperatures, we can do that at room temperature, and even ambient conditions, which is, for us, I must say, from experimental point of view, was quite remarkable, just because, imagine we have a single quantum well on the surface, ambient condition, there is no vacuum, there is air, and we pump an energy as high as several millijoules per square centimeter. It's quite a lot. It's usually close or above damage threshold for many systems. And there are two reasons why it sort of works in this type of material. First of all, we have sort of inert, of course they're not inert, but largely inert van der Waals interfaces. So all bonds are saturated, we have no dangling bonds. And secondly, because of the very close proximity to the substrate, the heat extraction is quite efficient. Yeah? And such a measurement, it goes easily over half an hour, because the way it's done, there is delay line, several pulses, and all of that, during all the time, the materials are radiated and illuminated with such pulses. Yeah? But it still comes back. If we look in a bit more detail what's going on here, and in this particular case, I show you the bilayer data. Again, there is some background from higher states and the exciton peak. And as the pump pulse arrives, just shortly after the pump pulse, we see again a complete bleaching of this exciton resonance, which was dominating the optical response before. Instead, again, it disappears, and from one energy on, we see sort of a very flat dip in the absorption spectrum. Again, we see a small recovery after a few picoseconds, and it recovers completely after something like 250, 300. To understand what's going on, we turn to basically to gallium arsenide physics, to what people calculated and also measured for the quantum wells. And the predictions were that in the lower density regime, the absorption, as I showed you before, basically is dominated by the very strong excitation resonance. There is a band gap, some excited states. Now in the high density regime, the absorption spectrum of such a semiconductor changes quite dramatically. And here again, what we did, we basically traversed the so-called mode transition. So right now, we don't have a carriers, and we have no ability basically to excite a bound exciton state. We have more or less like a fluid, a gas of electrons and holes. And if we think about screening, of course, the screening alone in this regime will make the Coulomb interaction ineffective enough to make the binding energy of exciton going to 0. We will have complete ionization of the state. Of course, thinking about fluids, there is still a correlation between the two. So if we would look, let's say, probability of finding a hole next to an electron, it will be still finite. Yeah, but there will be no bound state. Secondly, the way to think about it, that the attractive interaction, right, is now reduced because of screening, but so does the repulsive interaction. And in a very simple picture, the repulsive interaction between carriers co-defines the absolute energy of the band gap. Yeah? So if we look, let's say, at ab initio calculation on the level of DFT of a single particle, then think about the self-energy, which comes in on the GW level, that will push the band gap up. Yeah? And the stronger this repulsive interaction, the higher it will go. And now we sort of reverse this. Yeah? So we make all Coulomb effects weaker, also the contribution to the self-energy. It means the band gap reduces. And this is also what's expected and what calculated from the theory. So the band gap normalizes to lower energy, even beyond the exciton resonance. And finally, of course, we have carrier population. Yeah? So we pump so many carriers, we have chemical potentials on the order of hundreds of MeV. That means we have basically not only sort of bleaching, but even an effect called population inversion, which means, well, know from atom optics, that we have more carriers in excited states than in the ground state. So it means that roughly over this region, we will have basically electrons populating the conduction band and holes the valence band with very high probability. And in the absence of all other channels, of all absorption and scattering channels, that would be the regime where one could build a laser and we will have a gain and amplification. Yeah? And this is basically what we observed in the experiment. Very close to these predictions. We have the disappearance of the resonance, the dip, and the onset of the band gap over here. Yeah. And considering that we're starting with the exciton binding energy of a couple of hundred MeV, it means that the renormalization here is as large as half of EV. Yeah. So all these Coulomb effects are on the order of band gaps in such systems. And sort of in a very qualitative way, we can see it from the theory, because everything here scales with the binding energy of the exciton. So everything scales with the strength of the Coulomb interaction and as renormalization here. So with that, I would like to conclude my talk, and what I have shown you is some properties of atomically thin semiconducting layers with sub-nanometer thickness. I've shown you that the Coulomb interaction in these layers is extremely strong and also unconventional because of the screening, mainly of the weak dielectric screening and of this sort of near-field electrostatic properties of the system. That leads in particular to very close proximity of electrons and holes and a very strong light-matter interaction, as exemplified in the absorption spectrum. Binding energies of excitons, again, very, very large, many, many hundreds of MeV. And finally, they exhibit quite some electrical and optical tunability. I would like to thank actually quite a lot of people involved in this research over the last few years, just to highlight a few. So Tim Berkelbach contributed a lot to the theory of these particles. With Claudia Rupert, who is now at the University of Dortmund, who worked on the high excitation regime, and Aaron van der Zande made all the processing and the electrical part of the doping project happen. And there are a lot of more people here. In particular, I would like to thank Tony Heinz, who was a wonderful advisor over the last 3 years during my postdoc time there, as well as Mark and Dave, very strong support on the theoretical side, and of course Jim Holm for his contribution to the material side and the processing. And with that, I would like to conclude it, and thank you all for your attention. Thank you very much.
Thank you very much for a very clear talk, very interesting. Time for questions.
For some number of layers, the indirect gap and the direct gap are about the same. It's 2 layers or 3 layers or something like that.
So it basically, if we go beyond roughly 4 or 5 layers, it's basically like a bulk. Yeah. So the whole, I mean, the confinement effect more or less happens on the order of the last few layers. So if we look at 6-layer material and look at bulk, we will have more or less the same gap. So most changes happen on the order of just a few layers. Yeah.
And I mean, can you excite the indirect exciton? Can you get some things into the indirect?
Well, it's a bit tricky. So we don't get optics from that so much. I mean, of course we get emission, right? So we can get emission from the indirect band gap. This is fine, but it's very hard to do an absorption type experiment to look at all these higher states this way. There are other ways to probe it. Basically, one way nowadays available using strong and pulsed mid-infrared terahertz sources to probe the intra-excitonic transition. And it was done quite successfully in indirect gap materials, silicon germanium, for example. That would be a way to do it. Another way maybe some sort of photoemission spectroscopy, where we basically maybe 2 ppE sort of to map out the conduction band. This is insofar interesting because it's not only bilayer question, but what I have not mentioned here, one can actually put a lot of materials on top of each other, and in a very sort of forgiving way, because in terms of alignment of the lattice constant and this and that, because of the van der Waals interaction. And there are a lot of studies on all sorts of indirect, also excitonic excitation, which have the similar issues with smaller strengths. Well, we need to find other approaches.
Well, actually, maybe just to follow up on that.
Yeah, sure.
I mean, there are advantages of indirect semiconductors like silicon. If you pump them hard, you can, of course, get electron hole liquids. Are you sure you can't get those here?
Yeah, so the challenge is to some degree, at least as much as I'm familiar with the research in silicon in terms of this droplet formation, that you need to have relatively low densities and very high purity material in terms of the mobility and all of that, which is still a bit challenging in this type of material. So here it's easy to access all these high density regimes because the material is very stable, it's very thin, we can dope it electrically. It's more difficult, and similar as in graphene, where people talking about puddles, to have more or less a homogeneous low density excitation. But in principle, all these phenomena should occur here and be to some degree normalized. I mean, not only because of screening, but also because the interaction is not 1 over R anymore. And there are a lot of questions from us to our theory colleagues how it will affect.
Well, it's actually not obvious you get electron hole liquid because that mostly depends on there being multiple valleys in sort of lowering the kinetic energy versus the binding. So it might not work. So a separate question related to that, however. If you're just in the direct regime, how well nested are the electron hole Fermi surfaces? Are they pretty cylindrical?
They are so close to the minima. They are roughly cylindrical, but the further you go away, you start to see the implication of the hexagonal structure, and they have sort of mass anisotropy and things like this because of the symmetry. But that barely affects the region where we have our exciton wave functions.
But you have a sense of the temperature that you're at when you're pumping these things? Because, I mean, obviously you mentioned BEC.
Yeah. Well, I mean, the temperature of the gas we will get in our optical experiment will be rather high. So that one we will expect to be easily many hundreds, maybe even in the first picoseconds, maybe even thousands of kelvins. People try to go for BEC, of course, at more moderate excitation densities, but again, the same issue to balance the excitation with, basically also the many-body effects from the excitation with the density which is necessary to get a BEC. Maybe polariton, going the same way people did for gallium arsenide, starting with the polariton condensates will be an easier way, and then to see how we can get it without the optical confinement. Yeah.
Yeah, just, I hear a lot of discussion in these transition metal dipalcogenides about the importance of spin-orbit coupling and differences in spin-orbit coupling between K and minus K, and therefore, A, interesting spin states of excitons, and B, spin textures and magneto-optical effects. How much of that can actually be seen, and how much of that is just theoretical noise?
Well, I mean, first of all, I mean, you're definitely right. I mean, it's hard to say, but I would say at least like 1/3 of the groups working in this field are going specifically for the spin value properties. And specifically for excitons, it's sort of connected to your previous question. There are a lot that leads to sort of a lot of excitonic states and the multitude which are different, right? Singles, triplets, and so on and so forth. So the things people have done already is sort of more simple experiments. So looking at Zeeman shifts, looking at one recent one at the diamagnetic shift of the exciton, which is another way to sort of define and look for the Bohr radius. A few phenomena are a bit difficult to detect because of the line widths of the resonance, and you know, these very small shifts or very small splittings. And one of the reasons, of course, material quality, as usual, right? I mean, we're not in the same stage as silicon as gallium arsenide. The other reason is that because of the strong light-matter interaction, our intrinsic broadening is already easily a few MeV, which means certain effects will be hard. But for example, in terms of Bose-Einstein condensates, people are thinking about the triplets with potentially longer lifetimes to be a more appropriate system, the indirect excitons, and of course the possibility of using the valley as information carrier, which is sort of discussed, but of course right now is, let's say, when people were talking about 200 nanoseconds of lifetime, which is sort of still a bit too short. In the systems, we're not there yet.
Okay. Okay.
I wanted to return to the triumphs that you were mentioning.
Yeah.
Of course, they live in the gap, and I suppose they must therefore have infinite lifetime, technically. So can you dope into them? Can you produce a Fermi liquid of triumphs? Do you think that's theoretically possible?
So the trouble is they actually do not have infinite lifetime because they also can recombine optically. Yeah. Or basically through emission of photons. And
but they're charged. How can they recombine to give nothing?
No, they give the electron stays. So the recombination. So the trion you can imagine following. You have an excitonic core in a very sort of simple way, and the outer charge sort of orbiting it. Yeah. So the two electrons are not hybridized in a trion. And what happens when they optically recombine, the excitonic core, so to speak, the electron hops into a hole, emits a photon. The momentum is transferred partially to the remaining electron. Yeah. And that actually even gives and relaxes the selection rules for the recombination of the trions. Because the exciton basically, as long as when the excitons start to move, it cannot emit light. That's it, because it can't, its momentum is high enough. But for the trion, this rule doesn't apply. It can always satisfy the momentum relation by giving it the extra electron. What we can think about, with respect to trions, so now we have actually an opportunity to move excitons around. And for example, talking about light-matter coupling and Bose-Einstein condensates and polariton physics, for example, we'll have an opportunity to have a charged polariton, or a stable one. So we'll basically have sort of a particle which is half excitons, half electron, half photon, so to speak.
Well, I must have misunderstood something. I thought you said it lies inside the gap.
No, here, excuse me, may I say the problem is that the trion has a lower energy than the sum of an electron plus an exciton, which you could simply make the exciton go away, and the resulting one electron would have lower energy than either. That's why it doesn't. That's why it has
energy that's lower than the conduction band.
It will be promoted. So if we look very closely, and thanks Andrew for clarifying it a bit, but if we look closely at the spectra, if we look at this difference between between exciton and trion feature, it will resemble the core binding energy. What Andrew said. Of this extra electron only at zero doping conditions. As we increase the doping, this difference will increase, and the reason would be that a part of the energy we need, let's say if we think about recombination, we need to put the electron back at the Fermi surface, back at the Fermi energy, and that will give an additional factor. For example, we would see in the optics proportional to the distance of these two states. But the picture is always that the photon can be converted in an exciton, yeah, both in absorption and the other way in emission, but the trion forms by taking one of the free charges which are around and bind into it.
Okay.
Yeah. So maybe that's clarified.
Actually, I'd like to ask a question
Yeah.
on from that. So your transistor, so you created these trions with the transistor essentially by adding that extra electron.
It was more capacitive here
Okay,
in this
well,
case. But
okay.
yeah, you're right. You're right.
So what happened, but it didn't seem to be bipolar, so if you added a hole, you didn't see anything. Is that obvious?
So wait.
So if you go to the data, you had
I mean, if you make like, of course. So what people did, they basically provide an LED, right? So they inject both an electron and a hole. Oh no, you mean sorry.
The trion is
okay.
then 2 pluses and 1 minus.
Yeah. So this is possible. It's not technically possible for every flake we have because a lot of them are unfortunately doped to start with. So we need to sort of to drive our gate voltage back and to get to the neutrality point. But in the materials, in the flakes which are close to neutrality, you can access both regimes. The properties are very similar. The reason is that the masses of holes and electrons are very similar in the system. There are, of course, differences, and of course also because of the spin selections and sorts. But they are very symmetrical. So the positive and the negative trions are rather symmetrical.
Any other questions? Actually, I have maybe one more question, completely different about heat.
Yeah.
So you were doing this very intense business, and you said, on the kind of scale of picoseconds, you were pulling the heat out. So this is, you said the coupling to the substrate is important, but actually, what is often in a lot of these things, the phonon mismatch between the material and the substrate can be a real bottleneck. Do you know much about how you could potentially, get that heat away faster?
Okay, so maybe so first of all, I probably somewhat was maybe somewhat misunderstanding representation. I said so. The heat of the electronic system is very high, and that will cool down within a few picoseconds, usually by emission of phonons, not into the substrate yet. Yeah, it will still be in the layer, right? It will still be in the layer. The coupling to the substrate is such that if one measures it, and there are a few ways to measure this interfacial sort of heat conductance, you get a few hundreds of picoseconds for usual transfer times. It's rather similar to graphene, and that is one of the reasons actually, and I didn't talk much about it, but the recovery we observed at these time scales can and to a large degree will be related to cooling. It's still rather fast, in let's say comparison to if we have like a bulk, some buried quantum well, and it has to transfer in heat a lot. The context itself, of course, are not very well defined. Yeah, especially in the systems where we just exfoliate. So we had a rough surface, we have some atoms trapped in between. But basically, the proximity, in this case, that's the thing which helps. And the material will heat up. Yeah, the material within this time, and there are phenomena like Auger recombination, which are quite efficient in this density, which will very quickly get a lot of phonons into the system. That means that such experiment will easily heat up the lattice by maybe 100 to 100 Kelvin, yeah, for these conditions. In a more gentle experiment with, let's say, microjoule pulses, you will get just maybe 10, 20 Kelvin. Of course, depends on the temperature. Yeah.
What's the spot size?
Oh, the spot size, yeah, that's, so in this experiment was about 5-6 microns, which to some degree makes it challenging to work with because, of course, we're doing a probe experiment and things like this, so the number of photons will get is small. Yeah, but the heat, the most of the heat will go this way, yeah, not that way.
Okay, if there's nobody else, then I propose we thank the speaker and